right. Okay, so I think today we will just dive back into the material. So as a quick reminder, we're currently working through lecture set number 4. We are already at the 5th of March. So we are here today, March 5, 21. And we're talking about ratio estimation. So we have seen ratio estimation in two different situations. In the first situation, we talked about ratio estimation as a tool for estimating a population ratio, which would be a parameter that we have not seen until this particular unit. And that parameter defines essentially the average of the variable of interest divided by the average of what we are calling an auxiliary variable, where auxiliary really just means extra or additional. And this auxiliary variable, we assume or check to see, that's not the right way to phrase that, but when we include this auxiliary variable, it is because it is correlated with the variable of interest. So we can estimate the ratio of the means of these two variables. That's the first situation, and we talked about that last Friday and a bit at the beginning of class on Wednesday. And then we can also use ratio estimation to estimate the population mean. So this is a additional tool for us to find an estimate of a population mean. This particular strategy has been used within the concept of simple random sampling. So the idea is that we have collected a simple random sample, and for each observation in the simple random sample, we have two measurements. The first measurement would be the variable of interest. The second measurement would be this auxiliary variable. Okay. So we can also use ratio estimation to find estimates for a population total, tau, or a population proportion, which we can call pi or little p. Now you can imagine that the procedure for estimating tau is going to be very similar to what we saw when we estimated the population mean. So for example, on slide 22, we can show that an estimate of the total for the variable of interest is given by our population ratio, or our estimator for the ratio, multiplied by an estimate for the total for the auxiliary variable. And then we can show that the variance of this estimator has effectively the exact same form as the SRS variance of the total estimator, in that we take the portion that is related to the mean, which is the 1 minus n over little n squared, multiplied by sigma r squared over little n, and we're now multiplying by capital N squared. And this is a fairly straightforward derivation from the one that we performed for the variance of mu tilde y. Okay, so we'll work through a quick example to apply these two techniques, or to apply these two formula. So in this example, we have researchers measured the snout length and width of 15 alligators in Florida, estimate the total weight of the population of alligators with an approximate 95% confidence interval, and then assume that capital N, the number of alligators in Florida, is in the range of 1,250,000. So the purpose of this last part is basically to show that we're not going to need the FPC, because if you consider this fraction here, which is going to be 1 minus 15 over 1.25 million, this is obviously going to be much greater than 0.95. Okay. So we're going to be able to ignore the FPC when we get to the variance calculation part, but we do need capital N in order to compute the variance. Okay, now we're using ratio estimation. So we do require that the variable of interest, which is the weight of the alligator, and the auxiliary variable, which is the snout length of the alligator, are correlated. So if we consider the scatter plot that's given on slide 23, and we sketch a straight line through this data, we might have something that looks like this. And what we can see here is that it does appear as though the data follow this straight line relationship, right? So from a visual inspection, we have evidence of a positive linear correlation. Okay, so this would suggest that using the auxiliary variable will be beneficial to us. So we are gaining additional information by including the auxiliary variable in our estimation scheme. Okay, so we want to find the total weight of the population of alligators. So Y is going to be weight of alligators. X is going to be snout length of alligators. And then tau Y, I don't know why I wrote the T like a tau. Tau Y is going to be theta tilde multiplied by tau X tilde. Okay, so here we're going to have the ratios of the two populations. Okay, so this is going to be 4.418 divided by 3.758 multiplied by capital N and then in this case we actually have mu x. So since we have mu x here, we can get a direct estimate of the population total. So we don't actually need to use the estimator for tau of x. So then we can multiply this thing by 3.5. Okay. And this is going to give us something in the area of 5,141,784 pounds. Okay, so we also require the 95% confidence interval, which means that we need to compute the variance of tau tilde y, and then we will have to take the square root and multiply by 1.96. So now we will have the variance of tau tilde y is equal to n squared 1 minus little n over capital N multiplied by sigma r squared over little n. Okay. So we can ignore the finite population correction in this case for the reasons given above. So now we have this. Okay. So this is going to give us 1,250,000 squared multiplied by 0.325 squared divided by 15. All right. And then this value see if this works out. All right. So then we can say the standard error of tau tilde y is equal to 1,250,000 multiplied by the square root of this, which is equal to 183,995. Okay, so therefore the 95% CI is 5,141,784 plus or minus 1.96 multiplied by 183,995. And that should give us something in the area of 4,781,154 to 5,502,414. Oh wait, sorry, these, there we go. Yes, and yes. I actually, yeah, caught that one before I read it too. It is already squared. Okay, so I think that the in this situation, the estimate for the total, this concept is pretty straightforward, following from the estimate for the mean. So again, really, like all we're talking about here is multiplying by a factor of capital N, and then that capital N is accounted for in both the standard error and in the estimate for the total. Right. And again, just as a reminder, so this ratio estimation approach, this is both of this approach and the direct approach, which would be the SRS approach, both come from the same sample. So we could use the information that's given to us in this problem to compute the SRS estimate as well. But we're including the information from the auxiliary variable because it's shown to be linearly correlated with the variable of interest. So that's, again, the motivation for the inclusion of that value. But you can directly get the SRS estimator in the traditional sense just by focusing on the parameter of interest from the information that's given. Okay, so we're going to talk about ratio estimation for a proportion as well. And then we're going to start to talk about regression estimation. Now, the process of talking about regression estimation will be very similar to what we did in the ratio estimation case. So we'll introduce the idea, the motivation for regression estimation, which is very similar to that of ratio estimation, with the only difference being that we don't require the relationship to go through the origin. And then we will talk about the properties of the regression estimator. So we'll look at the properties of the mean estimator and of the variance of the estimator so that we know if it's unbiased or not, and if we can, how to bound those estimators, and then we'll work through some examples. So it'll be a pretty much the same step-by-step process to get comfortable with that approach as what we took with the ratio estimation approach. Just before we start that point, we're going to talk a little bit about bias in the ratio estimator. So just some things that we can be aware of that affect the reliability of our ratio estimate. Okay, so this first slide, slide 25 here, this is just a little bit of extra information, an alternative strategy, if you will, for calculating the ratio estimate. So since the ratio estimator is essentially an estimate that accounts for linear correlation between the two variables, but is required to go through the origin, we can actually show that the ratio estimator could be the ratio estimator could be calculated by taking the average of mu y, by taking the average of y divided by the average of x, or we could use a traditional least squares approach to find an estimate of theta, which would be the sum of xi yi over the sum of xi squared. So this is simply just an alternative way of calculating theta in the ratio estimation scheme. Okay. So we have two approaches essentially for computing the same estimate. So it might be of interest at some point to use both of those and compare them to see how close they are to one another. All right. So we know from our previous derivations, the ones that we started this particular lecture set with, that the ratio estimator for the mean, and then of course for the total, because they're effectively the same thing up to a constant, they are actually both biased estimators. So we found approximately unbiased estimates based off of a Taylor expansion around the point. Now, in general, we can say that the ratio estimator will generally produce a smaller variance than the traditional SRS estimator. So that does motivate its use. So the inclusion of a correlated auxiliary variable should allow us to have a more precise estimate of the population mean. However, it would be interesting to have some insight into how the bias is going to behave so that we know what factors in the experiment are going to increase or decrease the bias of our ratio estimator. Okay, so to calculate the bias of the ratio estimator, we can use the following relationships. So we can show that mu tilde ratio minus mu tilde, or minus mu, is equal to mu tilde y over mu tilde x multiplied by mu x minus mu y, which is equal to mu tilde y 1 minus mu tilde x minus mu x divided by mu bar x minus mu tilde y. Okay, and then what we can show is that the bias of mu bar y is equal to the expected value of mu tilde ratio minus mu, which is equal to the expected value of mu tilde ratio minus mu y minus the expected value of mu tilde y over mu tilde x multiplied by mu tilde x minus mu x. Okay, this is equal to the negative of the expected value of theta tilde multiplied by mu hat x minus mu x. This should be tilde. Okay, and that's equal to the negative of the expected value, or sorry, and this is equal to the negative of the covariance of theta tilde mu tilde x. Okay. All right, so from this, we can make a few clarifying points about the variance of our estimate here. Sorry, this is not mu tilde. These are all tildes. There we go. All tildes. Okay, so from this we can make a few clarifying points about how the bias of mu tilde y is going to behave under ratio estimation. Okay, so for example, in 1954, Hartley and Ross show that the absolute value of the bias of mu tilde y divided by the variance of mu tilde y is equal to is less than or equal to the square root of the variance of mu tilde x over mu x, which is equivalent to the coefficient of variation for mu x. Okay, so that basically what they're showing is that the absolute value of the bias of the ratio estimator is small relative to the standard deviation of the estimator if the covariance of mu tilde x is small, or if the covariance of mu hat x is small. So for a simple random sample, the coefficient of variation for mu hat x will be less than or equal to the variance of x divided by n times mu x, such that the coefficient of variation of mu tilde x will decrease as the sample size increases, right? So this is a pretty standard result, or kind of an expected result, in the sense that it's basically just showing us that estimation is going to improve as the sample size gets larger and larger. Okay, so this is more or less what we would expect to be the case for most estimators, but we can show through these relationships that this is in fact true. So the more information we collect, the better we expect our estimator to behave. Okay, so we can also show that the bias of our estimator for mu using the ratio approach is going to be equal to the term given here, and I'll just write this as a star so you know which term I'm referring to. Okay, so we can show that the bias of mu hat ratio is equal to the FPC multiplied by 1 over n times the mean of x, multiplied by theta times the variance of x minus rho, so the correlation between sigma x and sigma y, times sigma x times sigma y. Okay, so from this, we can make the following statements. Oh, sorry, 1 sec. Did I get ahead of myself? Yeah, I got a little bit ahead of myself. Okay, so from this, we can show the following: that the MSE of mu hat ratio is approximately equal to the variance of mu hat y about theta times mu hat x. Okay, which means that in general, what we can show is that the bias of mu hat ratio is small if the sample size is large. So again, this is kind of the general conclusion, or the expected conclusion, of how an estimate is going to behave when you collect a large sample. We can show that the bias is going to be small if the sampling fraction is large, which is the same idea, because this is basically if the sampling fraction is large, where large means closer to 1. So this is a value that's bounded between 0 and 1. Okay, if it's close to 1, that basically just means that you have a large portion of the actual population. So this is a very similar conclusion to what was shown in the first point. The bias is going to be small if mu x is large. That's an interesting result. The bias is going to be small if the variance of x is small. This again makes sense, because if you have precision in the auxiliary variable, you would expect that if it's correlated with the variable of interest, then you would have more reliable information being contributed to the estimation scheme, because those values are going to be closer together. And it's going to be small if rho is close to 1, which again, I think is an expected result, because if rho is close to 1, it means that those two variables are strongly correlated with one another. So they have a strong relationship. And given that that relationship is strong, the contribution of the auxiliary variable is going to be more beneficial to our estimation scheme. Okay, then we can also show that the mean squared error of mu hat ratio is small under similar or expected cases. So again, we have if n is large, if the sampling fraction is large, and if rho is close to 1. So again, these are expected results. If it's an unbiased estimator, the mean squared error is equal to the variance. So we're basically just saying that the variance about the estimator is small if we have a lot of information from the population and we have a strongly correlated auxiliary variable. And we can also show that the mean squared error is going to be small if the deviation of the variable of interest minus the ratio times xi is also small. Okay, so the purpose of these few slides was simply to give us a little bit more insight into how we expect the properties of our estimator to behave. And the reason that I wanted to go through this was, well, for that purpose, to give you more insight. But those leading slides where we had a little bit more of the mathematics behind getting down to these derivations, those are simply points that we need so that we can see these results. So slide 31 is effectively a summary showing us what we can learn from studying the bias of those estimators directly. All right, so returning back to our original style of problem, we're now going to look at the ratio estimator in the context of estimating a population proportion. And then we will talk about regression estimation. Okay, so on slide 32, we have the following illustration. So this data set was collected in 1994. The data here resulted from the researcher, Peart, counting the number of woody seedlings in pig projected areas under each of 10 sampled oak trees. Okay, so we have a sample size of 10. So you can see that we have 10 observations on the scatter plot here. Now, effectively, what each of these points are a count of the number of these woody seedlings. Okay, so these are all discrete values that are counting the number of times the researcher observed these woody seedlings on each of the oak trees. Okay. All right, so in 1994, she then counted the number of seedlings that were still alive after a drought in the area. So she went back to the same 10 trees and she counted how many seedlings were still alive. So we have X, which is the seedlings alive, and then we have Y, which I have written as the number of seedlings that survived in 1994. Okay. All right, so this illustration, what's interesting about this is just the ways that you can view the data. So again, we're measuring a count, right? So we have the total number of observations or the total number of seedlings across all of these 10 trees. So for example, if we look at the summary statistics, you can see for number of seedlings that were alive in 1992, you have 10 trees. You have a total of 206. So the 206 is actually the total number of seedlings that she observed across these 10 trees. Now we've computed an average from this, which would imply the average number of seedlings per tree. And then in 1994, when she went back and counted how many seedlings survived after the drought, you can see here that we have a total of 61, and now you have 6.1 seedlings per tree on average, even though the average is somewhat, it's an alternative way of looking at the problem. You're saying, you have 6.1 per tree, but in total there's 61 seedlings that are alive, but that isn't evenly distributed across each of the trees. Okay, so in this illustration, the trees are actually the data. So that n equals 10 are the number of trees that are in this particular experiment. But we're counting number of seedlings, but the seedlings aren't the actual data points. So this particular experiment can actually be viewed as what is called a cluster sample, which is something that we will talk about in the next lecture set. So lecture set number 5. And the clusters are essentially plots of land associated with each of the trees in this particular case. So if we wanted to estimate the proportion of seedlings that survived from 1992 to 1994, we can do that using a ratio estimation scheme that would unfold basically following from what we did in our estimation for the total example. So we can do something like this. So we would have theta tilde is equal to, or sorry, theta hat rather. Okay. So this is going to be 6.1 divided by 20.6. Which gives us 0.2961. And then again, like what you can see here, just to re-clarify this idea of the proportion versus the mean estimator idea. So our ratio here is equal to 0.2961, but this would be 0.2961 seedlings survived divided over alive, right? So this ratio is of the average number of seedlings that survived the drought. So, or the average number of seedlings that were remaining in 1994 divided by the average number of seedlings that were alive in at the beginning of the experiment, so in 1992. So in that sense, it is a ratio or a proportion of seedlings that survived this drought. So if you consider the values that existed in 1992 as sort of the full population of, well, we shouldn't use the term population, but if you consider that to be the number of seedlings that were subjected to this drought, then now you have effectively a proportion of survival across those 2 years. All right, so from this estimate, we can find the average number of seedlings that survived, or we can find the total number of seedlings that survived, or we can find the estimate of the proportion of seedlings that survived. And we can bound all of those. So we already have the first value, which would be the proportion of seedlings that survived across the 2 years. If we wanted to find an estimate of the average number of seedlings that survived the drought, we could use our typical ratio estimation approach. So we could say, you know, mu tilde y is equal to theta tilde times mu x. I guess this would actually be mu ratio, right? Okay. Or if we wanted to, we could do tau ratio is equal to theta tilde multiplied by n times mu x. Okay. So this would give us proportion of seedlings that survived. Okay, so here we have So you can see in the context of the problem, the units that are being used allow us to have an interpretation of that ratio that is different from the interpretation that we were using previously. But we can still end up with the same estimates of the mean and the total in this case, but we would just have the mean or the average number that survived across, say, the whole forest in this case, or the total number of seedlings that survived across the whole forest. If we consider little n, well, it's given that little n is a sample of 10 trees from the larger population of trees. And then all of these can be bounded in the same way. So for example, if we wanted to bound theta tilde, we have the standard error of theta tilde is equal to the square root of, how did I give this? Yeah. Okay, and so in this case, we'll have 1 minus 1 over mu x squared, 1 minus little n over capital N times sigma tilde r squared. So therefore, actually, and then this has to be, it's a standard error, so this has to be a hat. And we would have 20.6 squared multiplied by, and in this case, we're going to assume that n is very large. I don't think that we actually have, yeah, we don't have a population size. So under the assumption that n is really large, approximately 1, then here we now have multiplied by sigma squared, sigma r squared, which is 56.3778 divided by 10. And this gives us 0.11. Okay. And so now, because of the construction of the experiment, we actually have an estimate of the proportion of seedlings that survived, which we can bound in the usual way. But we've done that through just a direct application of our ratio estimation approach. Okay. And then again, from this, you can compute an average number of seedlings that survived across the entire forest. You can compute an estimate of the total number of seedlings that survived across the entire forest, and you can bound both of those points as well. All right. Sorry, does anyone have any questions? Okay. So what I would like to do then is with the remaining 10 minutes, okay, so first off, I'll just quickly wrap up or make some concluding remarks about the ratio estimation approach. And then what I would like to do is start the regression estimation section. But I think what I will do is I'll just kind of skip ahead to an example so you can see how regression estimation would work. And then from that, we can go back on Monday and derive some of the properties. But at least if we start the example today, that means that you can finish up the assignment earlier rather than having to wait to see an example if you want to see an example before we get there. So just quickly, again, these are just a few clarifying points. These are points that I've already made regarding the ratio estimation scheme. So for basically just ratio estimation in the context of simple random sampling, so the data has been collected in the same way that we discussed before, so via SRS. And theoretically, you could do this using a systematic sample as well, or using a stratified sample. And we will look at examples of ratio estimation within the context of stratification a little bit later. But the general idea is instead of collecting one measurement, you collect two measurements. The second measurement would be what we call an auxiliary variable, which just means additional variable. And this variable is correlated with the variable of interest. And we can exploit that correlation to find an estimate of the average or an estimate of a total, for example. Or if the data is structured in a particular way, we can use it to find an estimate of a proportion like we did in the previous illustration. Okay, so ratio estimation assumes that there's a linear relationship between x and y, and that relationship travels through the origin, which basically just means you have a line of best fit, but the intercept term is zero or not significantly different from zero. We can have situations where we have an auxiliary variable, but the linear relationship between the auxiliary variable and the variable of interest is linear, but does not pass through the origin. So regression estimation is basically just an approach that we utilize to find an estimate of, say, the average when the linear relationship has a real y-intercept. So you have x and y that are linearly correlated, but the intercept of that fitted line would not pass through the origin. Okay, so this is just a simple adaptation of ratio estimation when you don't have a line going through the origin. Okay, so the process of deriving this estimator is pretty straightforward. So essentially, we're going to assume that there's a straight line model that relates the variable of interest to the auxiliary variable. Okay, and that straight line model is given in 3, and you can see that this is just a linear regression model, a simple linear regression model. Okay, so from 3, we can show that since B0 is mu hat y minus B1 mu hat x, then the estimates of y can be written as mu hat y plus B1 times x minus mu hat x. All right, from this, we can show that a regression estimator for the mean is given in equation 5. So here we have mu tilde y plus beta 1 tilde minus or times mu x minus mu tilde x. So you can see that we require mu x in this case. And then we can write that beta 1 tilde is actually just the least squares estimator for the slope, which is sxy over sxx. Okay, so this is something that you can derive, and we have derived in stat 372 using, for example, maximum likelihood estimation or least squares estimation. So this is a very well-known result for the slope of a simple linear regression line. So this result here isn't something we need to worry about deriving directly in this class, but it is something you can work out pretty easily. All right. So we're going to talk about the properties of the regression estimator, but as I said, I just want to start by looking through an example of how this approach would work. So let's assume that we have a sample size of 15 university students, first-year university students, from a population of 68 first-year university students. We have two variables for each student, which are the number of hours they slept the night before a test and their associated midterm mark on that test. We want to estimate the average mark on the exam for all 68 students with a 95% confidence interval, given that the true average number of hours of sleep was equal to 6. Okay, so when we look at the scatter plot for this relationship, what we can see here is we have a linear relationship that does not pass through origin. Okay, now I admit that the scatter plot here doesn't show this as clearly, but you can just trust me in saying that this is a relationship that doesn't pass through the origin. The y-intercept here is actually somewhere in the area of 39.221, I think, is about where it is. So you have a line that passes through 0, 39. So clearly not something that goes through the origin. All right, so ratio estimation would unfold as follows. So we have mu tilde reg is equal to mu hat y plus beta 1 hat multiplied by mu x minus mu hat x. Okay, so from the scatter plot, we have mu hat y is equal to the sum of I, or from the table of the raw data, our estimate of mu hat y is going to be the sum of the yi over n, which is 71.8. And this is actually the same thing as the SRS estimate. So just like with ratio estimation, you can actually see that the SRS estimates are really being included in the estimation scheme. They're just kind of being adapted or manipulated, if you will, to account for additional information. All right. We're also told, or we can also show through the same strategy, that mu hat x is going to be 5.52. All right, now we need to compute beta 1. So beta 1 is going to be found by taking the least squares estimator. So this quantity here. And we can show that this thing works out to be 5.902. So we're computing an estimate for the slope of the line directly. Right? And then from this, we can show that the estimate of the average midterm mark for the full class of students will be given by mu hat y plus beta 1 times mu x minus mu hat x. So this is going to be 71.8 plus 5.902 multiplied by 6 minus 5.52, which is 74.633. Okay. Okay, so we still need to go through, we have to bound this, so we need to go through the derivation of the variance. So that's something that we can now do on Monday. So on Monday, we can talk about how we would derive the variance for the regression estimator, and then we can directly apply it in the context of this problem to bound the estimate. Now, with that being said, there is the estimate for the regression estimate, for the variance of the regression estimator, is given on slide 39. And this is the form of, again, that variance of the mean of the regression estimator equation. So if you're comfortable working with the summations, you can actually apply this directly and start to work through the variance, and then you can bound these estimators. But we will go through some simple examples of how this works on Monday, along with the derivations of those terms. But at the very least, at least this illustration gives you some insight into how the regression estimator approach works, which means that you can start to kind of push ahead into that third or fourth question on assignment 3, where you have to do the SRS, the ratio, and the regression estimator. And with that, I will obviously stop here because I'm a little over time. But if you guys have any questions, as always, please let me know. I have office hours after this. And otherwise, have a good weekend, and I will talk to you on Monday.